Okay, guys, this question asks us to take a look at a heating curve. We're going to take some ice, it's minus 25 degrees C. We're going to heat it up to water at 0 degrees C. Now, all heating curve problems are the same. So in general, there's going to be some spots on this graph that I need to consider. Now, I'm going to be heating up the ice from 0 degrees C to, or from negative 25 to 0 degrees C. So I'm going to need that part of the heating curve. I'm going to also take the ice and I'm going to melt it. So I'll need this part. When you melt the ice, it doesn't change temperature. The energy just goes into melting. Then once it's liquid, it continue to add energy, and then the temperature does increase at that point. And once I reach the boiling point, as I add energy, then the substance boils or vaporizes. It doesn't change temperature, but once it's completely vaporized, then as I add more energy, the temperature does go up. And so there's 5 different regions: Q1, Q2, Q3, Q4, and Q5 in a general heating curve. And so in order to get the total amount of energy that it takes, you add up all 5 of these points. Now, in this problem, it says I'm going from negative 25 to 75. So that means Q1, Q2, and Q3, because I'm not going to get to the boiling point. So I don't need Q4 and I don't need Q5. And so I'm going to go ahead and just add this other point along the graph, 75 degrees C. And so I'm going to get rid of those last 2 parts of the sum. I only need Q1, Q2, and Q3 to add up. So what does my problem give me? It gives me all of the information I need in order to do this. So let's take a look at Q3 and Q1. These are standard heat flow calculations. Q equals M times C, specific heat, times the change in temperature. The only thing is that the specific heat of ice is different than the specific heat of water. So I just needed to do 2 separate calculations. Now for Q2, I need just a little bit of a small variation. I'm given the delta H of fusion, so I need the number of moles. The number of moles times the delta H of fusion will give me that heat flow for that piece. And so I need to go ahead and change it from, or convert it from grams to moles. And I'll use the molar mass of water to do that. So I get 7.214 moles, and the 1 is the sig fig. So let me move this out of the way. Let's do Q1. So 130 times 2.18 joules per grams degrees C. T final, that's 0 degrees Celsius, minus T initial, negative 25 degrees Celsius. And so 0 minus 25 is plus 25. And so all said and done, I get 7,085 joules. So let me do Q3. I know I labeled that Q2, but it's really Q3. So 130 times 4.184 joules per gram degrees C. T final is 75. T initial is 0. So the Q3 total is 40,794 joules. And again, that's Q3. Now let's go ahead and go back and do Q2. That's 7.214 mole times the delta H of fusion, which is 6.02 kilojoules per mole. Mole's going to cancel. And I get 43,430 joules, with the 4 being the sig fig there. So now I've independently done the calculations to get all 3 of those things. So the total energy is the sum. So QT equals Q1, which is 7,085 joules, with that being the sig fig, plus Q2. Now Q2 is given to me was given to me in kilojoules, but I went ahead and converted it to joules here. It would have been 43.430 kilojoules. And so I did convert kilojoules to joules without mentioning it before. The units for addition do have to be the same, so I need to do that conversion. So 43430 joules, with the 4 being the sig fig there. Okay, and what do we got here? So then I've got the next one, Q3, 40,794 joules, with that being the sig fig there. And so when I add them all up, I get Q total equals 91,400 joules. And that is the final answer. Okay.